All right, let's talk about that dreaded support ticket, the one that just says the website is down. We've all been there. Well, today we are going to pull back the curtain and demystify what really happens when someone hits enter on a URL. This is for all of you in the trenches troubleshooting these exact problems every single day. So here's our roadmap. We're going to follow a single web request from the very beginning, that keystroke all the way to the server and back. And trust me, once you understand each step of this journey, you'll be able to pinpoint exactly where things are going wrong. All right, let's kick things off right at the start. You know, every single thing you do online, whether it's loading a homepage or submitting a complex form, it all begins with this one simple action. But that single click, it kicks off this insane, lightning-fast chain reaction across the entire internet. So let's actually look at what's happening under the hood. Let's break this journey down. This isn't some kind of digital magic, you know? It's a completely logical flow of events. And it all starts with your browser having to figure out, where on earth am I supposed to go? So before your browser can even think about sending a request, it needs an address. But not the friendly name you just typed in. It needs a specific set of numbers to work with. And this is where DNS comes into play. Honestly, the best way to think about it is that it's literally the phone book for the entire internet. It's this massive global system that takes the name you give it and translates it into the IP address the network actually needs. And thank goodness it exists, right? Because can you imagine having to memorize those long strings of numbers for every site you visit? No way. And this all happens in like the blink of an eye. First, your browser checks its own memory, its local cache, to see if it's been there recently. If not, it starts asking around, escalating the question up a chain of servers until it finds the one that holds the official, authoritative record for that domain. Now, here's the part that is absolutely crucial for anyone in support. When you update a DNS record, it doesn't happen everywhere instantly. That change has to spread across the globe, and that's called DNS propagation. This delay is the #1 cause of those "it works for my coworker, but not for me" tickets. A little pro tip: when a customer reports this, have them check a site like whatsmydns.net. It can show them in real time how that propagation is going. This table, this is basically your secret decoder ring for any DNS ticket. You see an NX domain error? That just means non-existent domain. It's almost always a typo. But a serve fail, that points to something deeper. The domain is real, but the server that's supposed to have the answers is failing or misconfigured. Okay, next step. Our browser has the IP address. Fantastic. Now it needs to actually open up a line of communication and connect to that server. You can't just start shouting data into the void, right? You need a stable, guaranteed connection. And for that, we have this elegant little dance called the TCP three-way handshake. Its entire job is to make sure both sides are ready to talk and that the line is crystal clear. It really is like a quick, polite phone call. Your browser sends a message saying, "Hey, you there? I'd like to talk." That's the SYN packet. The server gets it and replies, "Yep, I'm here and I'm listening." That's the SYN ACK. And finally, your browser says, "Perfect, I'm starting the conversation." That's the final ACK. And boom, the connection is live. Okay, now this is a huge one for troubleshooting. A connection timed out error. That feels like your request just vanished into a black hole. It never got a response, probably because a firewall ate it. But connection refused is totally different. That means you successfully knocked on the server's door, but it immediately slammed it in your face because the service you wanted wasn't running. So we've got the address, we've opened a solid connection, now it's finally time to ask for the website content. So that TCP connection we just made, think of that as the phone line. Now we need a language to speak over that line, and that language is HTTP. It's how the browser asks for things and how the server sends them back. So the browser sends a really specific message. It starts with something simple, like "get me this page." Then it sends a bunch of headers with extra info, like the user agent, which says, "Hey, I'm a Firefox browser on a Mac." And these headers are so important for support. You might run into a weird firewall rule that's blocking a specific user agent, which explains why a site works for one person but not another. Okay, so we've seen how it's supposed to work. Now for the fun part. Let's put this all together and see how it helps us solve a real problem. Ah, yes, the classic. The ticket that we've all seen a million times. It's frustrating for the user and can be a real headache to debug. But now, instead of just guessing, we have a logical framework to follow. First things first, we start at the very beginning of the journey. We always start with DNS. Can the user's computer even figure out where to go? Given that ticket, This is suspect number 1. That DNS propagation we talked about, this is what it looks like in the wild. If the A or AAA records, the pointers to the server's IP, were just changed, you've probably found your culprit. The coworker's internet provider has the new, cached IP, but your user's provider is still holding on to the old one. That's it. That's the problem. Okay, but let's say DNS is totally fine. Everyone has the correct IP address. What's next? Well, we just moved to the next step on our journey, making the actual TCP connection. When you ask these questions, you're basically replaying that three-way handshake in your head. If a ping fails or you get a timeout, something is blocking the path. That screams firewall. If you get connection refused, you know the path is clear, but you need to get on that server and check if the web service itself has crashed. And that's really the whole point here. This isn't just theory. It's a practical, repeatable way to troubleshoot. You just start at the beginning of the journey and test each step. No more shooting in the dark. So now you have the map. The next time that vague "it's down" ticket comes in, you'll have a powerful model to guide you. By systematically checking DNS, then TCP, then HTTP, you're going to move past the guesswork and become a way faster, way more effective troubleshooter. Thanks for watching.